So, first of all, I would like to really thank the organizers for this opportunity, and also I really want to apologize. I'm not able to be there in person, but I'm growing a human seed, and this is going observable directly. So it was really impossible this time. But I hope I will still manage to make you interested about what is the mergers and dynamics of massive black holes. So first of all, I would like to start with a bit of context. Of course, we all know that we expect galaxies to aggregate hierarchically. We expect and we observe also massive black holes to be in several galaxies already at pretty high redshift. We observed many times in the last days. And so this leads to the conclusion that many times at least two massive black holes could find themselves inside the same galaxy host, galaxy merger remnant. And this is very important in the context of gravitational wave detection. Because if we look at, for instance, this is the mass function, the number density of massive black holes. We see the stellar black holes and the massive and supermassive black holes. And actually, those massive objects are going to be observed in the future, and somehow they are already sort of observed today through gravitational waves. And in particular, if we really look at the very high mass end of massive black holes, we had very exciting results from pulsar timing collaborations all over the world a few months ago, and we have the hint of the fact that we may be observing a gravitational wave background that is in fact produced by inspiraling massive black hole binaries. And on the other hand, if we look into the lower mass regime, let's say the intermediate mass regime, then future observatories as LISA are going to observe, to detect the mergers of those objects all the way up to the onset of structure formation. So this is going to be very exciting to really understand what is the growth and evolution of massive black holes across the cosmic times, also in light of what we heard in the last days. Is going to be a revolution for our understanding of the history of massive black holes inside their hosts. But of course, if we want to understand those objects, we also need to really have a very good understanding of what is the path to coalescence. So what happens between the galaxy merger that occurs at large scales, all the way down to the gravitational wave-driven merger of the two black holes themselves. And of course, the processes that will influence the shrinking of those two black holes will have an impact on the final chirp mass, mass ratio, eccentricity, spin, and so on, that are going to possibly be measured by future gravitational wave facilities. So, of course, the questions we really want to answer are like, how much time do we need from the galaxy merger to the massive black hole merger? What are the processes that come across to help the binary shrinking or not shrinking? How do the binary orbital properties change along the spiral? And also, how does the mass and the spin of the two black holes change in the process? And of course, here we are talking about a very huge range of scales. And you can imagine, we had already several talks focusing on aspects that are related. There is no simulation that can cover the entire range of scales, because we have the of course, if we want to do everything very well, we want to start from cosmological simulations, but then those have resolutions that hardly go much below 1 kiloparsec. So we have to go into zoom-ins, and at some point we have to simulate a single galaxies or single systems. And this is, of course, very hard because we have to put together many different pieces. Of course, there are still many open problems also related to the fact that we still are struggling a lot in modeling this process from the large to the small scale self-consistently. But so how I decided to structure this presentation today is that I will first focus on typical pulsar timing array sources, just because those are the easiest to understand and to study. We are talking now about the massive black holes above 10 to the 8 solar masses, which enter the gravitational wave signal for pulsar timing array that have nearly equal mass and are found at a redshift below 1. So basically, we are talking about very massive elliptical galaxies with little or no gas and star formation. And later on, we are going to cover more complex LISA sources. So if we focus on those simple sources, we can divide the path to coalescence in simple stages that have been put forward already from the 80s, from this seminal paper. And we have dynamical friction, stellar hardening, and gravitational wave spiral. And I will quickly go through all those steps. So the dynamical friction, I'm sure nearly all of you are familiar with this phenomenon, is a sort of gravitational drag against stars that make each black hole that is sinking towards the center slowly lose energy and angular momentum, and we can think about it as a sort of drag induced by the overdensity of stars that can accumulate at the back of black hole that is spiraling down. And I just want to quickly mention, even if we are focusing on PTA sources here, that the formula for dynamical friction is very similar also if we consider a gas-dominated background, as it has been shown by Ivo Stryker in 1999. So if we look at the typical in spiral, the distance as a function of time for a massive black hole in a merger simulation, then we see this regular decay. Of course, there was some initial eccentricity, so it's not a monotonic decay. But we don't see any major weirdness, let's say, in this evolution. Already here, though, we have to be pretty aware of the fact that applying the typical dynamical friction timescale formula, it may be an oversimplification, because of course what we have to think about is that in the beginning we have a galaxy that enters the potential of another one, and this galaxy can be tightly stripped and lose its mass. So the effective mass undergoing dynamical friction gets lower and lower. And this, of course, needs to be considered. On the other hand, also the density profile of the host galaxy is very important to consider, because it has been shown, for instance, that even in pretty simply modeled galaxies, if the stellar or even dark matter profile is not cuspy, but instead it shows a core, for instance, several local dwarfs appear to be a core dominated in their dark matter profile, then what can happen is that there is a stalling of the binary of the two black holes at large separation, and they don't really manage to form a binary. So even in this simple picture, we have to keep in mind that there are some caveats. But so let's say, as in most cases, we would have our binary to efficiently form. And when the Keplerian binary forms, the new mechanism that can help the shrinking is the so-called slingshot ejections. So what happens is that each time a star comes close enough to a binary, then basically it gains energy through repeated interactions. It is kicked away from the binary system, and as a result, the binary shrinks its semi-major axis. And if this happens many times, as many stars encounter the binary, then the binary can efficiently harden and shrink. And the cool thing is that we have actually observational evidence of this happening, because many massive ellipticals nearby are observed to have chord central regions, and this is expected to be the effect of this slingshot of the binary, since those massive ellipticals have likely experienced a large number of mergers. And in the same systems, it has been shown that there is often a prevalence of tangentially biased orbit versus radial orbits, still hinting towards the effect of this slingshot ejection that basically selects the stars to be expelled as the radial ones. And so also in this context, I really want to stress again something related to the final parsec problem, because I'm sure many of you have heard about this problem, and perhaps not everyone is aware of the fact that nowadays this is not considered to be a problem anymore. And the sense of this is that basically the final parsec problem stated that many binaries would stall at roughly parsec separation because not enough stars were able to interact with the binary, so the binary would never enter the gravitational wave dominated regime. But this is not true, because if instead of simulating those binaries evolving in perfectly spherical systems, we allow the host galaxy to be triaxial, then the families of orbits that can interact with the binary are much more varied, and as a result, the binary shrinking can basically be sustained all the way down to the gravitational wave-driven regime. So this is not a problem anymore. And so, okay, maybe in the interest of time, I will skip this. And this was basically the simple steps that a binary in a PTA-like source would have to go through to reach its final coalescence. But let's now focus on the more complex LISA sources. Here we are talking about systems that are more like dwarf galaxies with 10 to the 4 to 10 to the 7 black holes, that we are observing systems that all the way up to the beginning of galaxy formation. Those galaxies are going to be very irregular, possibly heavily star forming with possibly a lot of gas, and very dynamical as environments. So the modeling of those systems is going to be more complex. And in fact, here I'm showing again what I showed you before. So the different processes that can help the binary shrinking from large to small scale. And here we can see that there are many more processes intervening, and these need to be taken into account. And I will try to quickly summarize what are the key features that change the picture that I described before in the case of LISA sources. So let's start from this, which is the case of the large scaling spiral. You remember that before, if we focused on the dynamical friction-driven evolution, what we would have is basically a simple timescale prescription, so to say. But here, what I'm showing as a representative example, but there are many other works showing the same thing, is the evolution of massive black holes in a typical galaxy that is very gas-rich at redshift 7 to 6. What I'm showing is the evolution of the distance as a function of time of three massive black holes in this galaxy that started basically with the same orbital properties in the plane of the disk, just with a different orbital phase. And in the same time scale, two of them made it to the center, while another doubled both in its initial separation and semi-major axis from the center. So this hints towards the possibility that dynamical friction is too simplistic as a treatment to study those complex systems. And in fact, what we found out is that if you measure what is the dynamical friction driven torque that affects the black hole that is in spiraling, this is much smaller than the global torque that arises from all the asymmetries like bars, spirals, like other galaxy flybys that are really strong, those additional torques in such a dynamical environment. And this randomizing effect is very important to take into account because it means that the spiral time cannot be as easy to predict as we would have expected if we were to only consider dynamical friction. And there are, as I mentioned before, several other works. Here I just mentioned a few that show analogous results. And of course, this effect is especially important for massive black holes that are relatively low mass, because dynamical friction is going to be less and less important. So their sinking is hard to treat. And here I'm just mentioning a few of the sources of this torquing that can in spiral very stochastic. For instance, in this case, we had this work in which we just studied the evolution of massive black holes in spiraling in a galaxy that was very smooth and totally like the Milky Way, so no super weird density distributions, but just with a bar in the center, rotating as the Milky Way one. And just including the presence of this bar, we found that the spiral time can change significantly. So even this simple morphological feature can have an effect on the spiral time, let alone if we consider the possible presence of clumps, for instance, that are observed in galaxies at a redshift close to 2. If we have those massive star-forming clumps that can be the same mass or even more massive than the black hole that is trying to spiral, those can kick the black hole around even out of the disk plane if there is a disk. And so the spiral can become very, very erratic. Here you see again the distance as a function of time. Sorry, this is cut. That's the distance. And also it has been shown that even in the presence of gas, gas in principle should help dynamical friction because the massive black holes would suffer friction from the gas itself. However, the fact that the black hole accretes and there is feedback occurring, of course, can have an impact on the dynamical friction. We can eventually get to the opposite sign. So instead of a dragging force that helps the black hole sinking, it may instead make it stall. And this has been shown, for instance, in this work by Lilly, that as a function of the binary mass, shows the pairing probability in a series of runs that either include or do not include the radiative feedback. And when radiative feedback from the black hole is included, the spiral is much less efficient.
Looks like you have 2 minutes, sorry.
Yeah. Sorry?
You have two minutes left.
Okay, thank you. Yeah. So in those irregular galaxies, the spiral is very stochastic. And I just want to add to this that this is not just impacting the evolution of binaries, but in general, even the fact that massive black holes hardly sink or hardly stay put in the center of their host galaxy, you can imagine can have important consequences for their accretion and their growth. And for instance, in this work by Amy Raines, it has been shown that in local dwarfs, often AGNs are observed not to be placed in what you would define as the center of their host galaxy. So this is an effect important in many different ways. And then, as the last thing, I want to mention that if our binary manages to form a Keplerian binary in spite of all those troublesome steps in the evolution, then, of course, we are still going to have the three-body interactions that I mentioned before, but we are also going to have possibly interactions with a circumbinary disk because a lot of gas is present in these sources. And in the beginning, it has been thought for many years, actually, that the presence of this disk would help the binary to shrink and even solve the final parsec problem when it was thought to be a problem. At the moment, though, it has been shown that in some specific configurations of disk mass ratio of the binary and thermodynamics of the disk, the presence of this disk of gas can even promote the binary out spiral instead of in spiral. And there is a lot of ongoing research trying to really understand what happens in the presence of these circumbinary disks. I don't have time to go into the details of this other study we did, but just to mention that we did a study in which we included both the effect of stellar interactions, gas-driven expansion, and the gravitational wave emission. And what we found is that even if you account for this possible expansion due to the presence of the disk, the binary would manage to merge because the stellar hardening is important, and also the mass growth promoted by the circumbinary disk presence can really help the binary to enter the gravitational wave regime earlier. And with this, I conclude, and I leave you here my summary slide, and I thank you so much for your attention.
Thanks so much for the wonderful overview, Elisa. Any questions?
Yes, thank you for the excellent talk. In the simulation where you show the in-spiral in the presence of a bar, does the speedening up of the in-spiral depend on whether the initial phase of the black hole is prograde or retrograde with respect to the pattern speed of the bar, or is that not a significant factor?
Oh, yes. So we studied also that. What we found is that basically if the black hole is prograde with respect to the bar rotation, then you have an effect that is much stronger compared to the retrograde case. And this is just because if you are in a retrograde configuration, of course, let's say the interaction time scale between the bar and the black hole is much shorter because the relative velocity between the two becomes larger. And as a result, in the retrograde case, the bar does not have such a dramatic effect. Did I answer your question?
Yes, thank you. Thank you.
Yeah, thank you. Great. Any other questions? Well, I will ask a question. You mentioned that the circumbinary disk can both expand and shrink the binary in different simulations. What do you think is the source of these discrepancies?
I mean, I'm not sure I can talk about the discrepancy what is my understanding, even if this is a bit out of my main expertise area, is that depending really on the thermodynamics of the disk, you can have different effects. So what I got is that the source of expansion, which basically implies a positive torque dominating the evolution of the binary due to the disk, is sourced by those mini disks. And of course, the properties of those mini disks depending on how the gas basically leaks from the cavity that is inside the circumbinary disk and reaches the mini disks. And what I understood is that you can have expansion basically only if the two black holes have a similar mass, so mass ratio close to 1, and also if the disk is, let's say, hot enough. If you have a thin cold disk, then it's much harder to get an out spiral. And also the disk should be basically not so self-gravitating. So you should be dominated by the potential of the Keplerian binary, so to say. So under these conditions, not necessarily all works agree on the fact that there is an expansion, but there is a decent agreement on the fact that there can be. Instead, in other configurations, for instance, if the mass ratio between the two objects is very far from unity, then I believe my understanding is that all studies find an efficient spiral instead. Does this answer your question?
Yes. Great, thank you. Yeah, one.
Hi, so it sounds from the summary that you expect a lot of binaries to have stalled and not merged. Do you have a sense of the statistics of this, as a function of, galaxy mass of some kind? And second, if you have so many binaries, and especially with circumbinary disks, do we have a sense of how much this can contribute to the variability that we observe in AGN?
Oh, wow. Okay. This is not, those are not easy questions. I will do my best. Regarding the statistics, well, unfortunately, I'm not myself a master of statistics of mergers. Possibly there are more expert people in the audience, actually. But what I can say is that most of the studies that really try to understand the statistics of this have a hard time in including all those processes. So for instance, all the sources of stochasticity that I described close to the end are hardly included in, for instance, semi-analytical models that we heard about, for instance, yesterday, and those are great to make statistical samples of black hole mergers. I think we are still kind of struggling in the modeling since we don't have a very clear and complete picture to really have a complete understanding of what is the effect in the overall statistics. That is at least my my thought about this. And then the other was about the variability. Can you repeat, sorry?
Yeah, the question was how much of the AGN variability that we observe might be produced by or in the circumbinary disks?
Well, it could, in principle, I think could be quite a lot. To be fair, this fact that the binary can, in some situations, expand would, of course, enhance our capability of detecting those binaries, because, I mean, what you have is that I didn't have time to go through this, but basically, in order for the binary to expand effectively, you need it to accrete a large amount of matter and a high Eddington ratio. And here is the Eddington ratio you need at least to expand the binary as a function of the binary mass. So you would have highly accreting binaries that can expand, otherwise you don't have enough gas to promote the expansion. At least this is what we found in this work. And if the binary stays there for a longer time due to this expansion, this of course would enhance the prospects for detecting those objects as variable sources, because for instance, what I'm showing here is for different binary masses that are different lines, and as a function of the Eddington ratio at which the binary is accreting, how this in spiral time varies. So here it would mean the binary does not accrete, and as we move to the right, it means it accretes more and more. And at some point, we see that the in spiral time has a maximum close to the stage in which the binary accretes close to Eddington. So if the binary accretes close to Eddington, it means we can have our maximum prospects of detecting those sources. So this somehow can be a good news, because anyways, the spiral time of binaries remains always much less than a Hubble time. So we never have a definite stalling, just a delay in the spiral. At least that's what we found in this specific work. Does it answer your question?
Yes, it seems to have. Okay. I think we should wrap it up here because we need to move on to the next talk. Thanks again, Elisa. That was a really great review talk. Okay, next up we have Jordi Davila. Jordi, can you share your screen? Yes.
Should work.
Great. I will also give you a 2-minute warning. Take it away.
Thank you. Yeah, thanks the organizers for having me at this workshop. I'm very happy that I could participate, although I am from Flatiron. I'm unfortunately in Europe at the moment, so I couldn't join in person. But I was asked to give a short talk on the electromagnetic signatures of massive black hole binaries. This is work done in collaboration with Zoltan Heyman at Columbia, Jonathan Schrake, Andrew McFadden, John Ryan Westernacher Schneider, who's a postdoc in Europe, and my Columbia graduate student, Luke Krauth. So that actually nicely connects to the talk that Elisa just gave, where she went from all the way from kiloparsec to smaller and smaller scales. Here I am at like close proximity of the two black holes, and then how can we detect them in other channels than just gravitational wave emission, which is important for host galaxy identification to understand where these massive binaries form and how black hole growth proceeds. So how do we currently tell that AGN potentially have a black hole binary, which nicely ties into the last question of the previous talk on the AGN variability? Well, there is some telltale signatures that people look for. And one of them is, for example, Doppler modulation of the overall light curve. So an example of that is shown here on the right. I think this is PG 13 something. It's a paper by Dan D'Orazio where he did optical monitoring of this source. And I'm not sure if I can show my... I somehow lost my tracker. Anyway, you see that there is this sinusoidal behavior in the light curve, which is attributed to one of the binary components either moving towards or away from you. But however, there is some ambiguity here for candidates, but they're still candidates because great paper by Vaughan et al. In 2016, where they made the excellent argument that in the case of AGN, like single AGN are also perfect binary mimickers if you only have 1 or 2 orbits measured. And how is that? Well, the red noise power spectrum of a quasar can nicely mimic long-term variability where there is some short-term variability on top of that. But here on the right, on the top panel, the The red line is what it would be if it's purely Doppler modulated. And then the bottom two, the pink line is representation of one of these red noise models, which equally well fit the data shown in blue and black. So to be able to discriminate between these two, you need to measure these potential candidates for many more orbits, but that's hard because these 10 to the 9 solar mass black holes have typically orbits of a year or more. So is there another mechanism that you could look at? Well, maybe yes, but this is, however, a pretty rare case. This is my favorite binary candidate, which is called Spiky, also known as KIC 11605854. It's a Kepler source measured in 2010. And the nice thing here is that besides this sawtooth pattern that you see in the black dots, which are all Kepler data, there's like this massive spike at the moment where the modulation of the eccentric binary goes to 0, so that means perfect alignment. You see this sharp sudden increase and decrease, which the authors argue is potentially caused by the eclipsing binary that gives gravitational self-lensing. So this is all interesting, but their model only did some very simple semi-analytical modeling of the self-lensing, although the binary is pretty close in, and there's all kind of also strong gravitational effects that they ignored because of this. So it's like a very simplified, a more simplified model than we could potentially do with the current methods. So yeah, I think Alisa already covered like the second part, so I will skip that for now. So how did we proceed then in that case? Instead of using like analytical formula to describe the self-lensing, we instead did a full general relativistic ray tracing simulation of a black hole binary. So what is this ray tracing? Ray tracing means that if you have a predefined model where you have some emission being generated around these two black holes, you can compute the amount of emission on the camera by integrating geodesics. So this camera consists out of pixels. Every pixel is assigned a wave vector. We put this wave vector into the geodesic equation, and we integrate that toward the source until it hits the accretion disk. And this is where we add the amount of emission that is being generated, and then we transport that to the camera to understand how much emission we measure. So here on the right, you see an example for that, for more like an EHT-like target. So you see like there's like this thick accretion disk around it. The left side is brighter than the right side, which is because of Doppler boosting or deboosting. And in the center, you have this darkening, which we typically call a black hole shadow, which is in essence, the gravitational cross-section of the black hole, or like a lensed image of the black hole's event horizon, which is around like 5 gravitational radii in radius. And this will be an important concept, this black hole shadow, because it will pop up later in the talk as well. So I said like, okay, this is like the example I show here is a single black hole, right? So instead of one black hole, we actually have a metric that describes 2 black holes, and they start orbiting around each other during our simulation. So what are the model assumptions we put into here? Well, the orbit is purely Keplerian. This orbit can be tilted with respect to the observer. The orbit can be eccentric. Both black holes have their own geometrically thin disks, which are emitting thermal black body radiation. We either set the opacity to very high or to 0, so that we can also mimic some form of like coronal component instead of just like a thermal black body disk. And the disks extend from either the horizon or the ISCO up to the tidal truncation radius of the individual disks. The tidal truncation radius just means that that's roughly how big these tiny disks extend. Otherwise, they will be pulled apart by their companion. And both black holes are also allowed to have black hole spin, so the amount of black hole rotation. So these are a lot of parameters. In total, we did like 27 different models, which is of course way too much for the remainder of like 5 minutes that I have left. So I'll just try to focus on the main takeaways of the papers that we had published last year in PRL and PRD. So to just give an example of how such a system looks like if we actually evolve it, it's also important to note that there's no time variability in our models, in these models that I will show, because it's just a pure Sakharov-Sunyaev style thin disk, which is purely radial dependent and not time dependent. So if I will press play here, you will see that the left black hole will start to move in front of the right black hole, where they swap left-right, and then the background black hole is being lensed by the foreground black hole, where it nicely curves around it. You get like this Einstein ring deformation of the background black hole. So that all looks very pretty, but what is the kind of science we can actually do with this, because we're never going to resolve this because these systems are very far away, but we can measure the total flux that such a system generates. So if we then start to look at light curves, so this is a system that is perfectly viewed edge on, so at a 90 degrees inclination with respect to the orbital axis. The binary has a separation of like 100 gravitational radii. It has an equal mass, and this is like around X-ray. So here on the bottom, you see a light curve as a function of time. So it's the amount of flux that one would measure as a function of binary phase. And then there are a couple of numbers here because there's an interesting feature that I didn't expect. So at like a quarter of the phase and like 0.75, you see like these spiked features, which are a bit looking familiar to what we saw in spiky. But however, there's like this dipping feature in the center, which I first thought, oh, maybe my code is wrong, or just misunderstanding what is happening. Well, it turned out to be the latter, because if you then match like the top panels, like 1 is right before they're perfectly aligned, 2 is also right before they perfectly align, and 3 is when they're exactly aligning. So what is happening here is the foreground black hole acts like a lens, and it's lensing an image that is moving through its focal point. So first it hits the left part of the ring that the background black hole generates. So there is something to amplify there. And then in the center, there's this darkening, so there's nothing to amplify anymore. It goes down, then it finds the right side of this ring, and there's amplification again. So this dip is actually a telltale signature of the binary lensing itself and imprinting the black hole shadow into a total integrated light curve. So I thought it was pretty cool because black hole shadows are a way to constrain GR. If you know the mass of the black hole, which we could know based on the periodicity of the signal, and if you then measure the black hole shadow, you could potentially put some constraints on GR if you can accurately measure that. It's like similar to what the EHT does. The only difference is EHT at this point can only maybe resolve 2 sources for the black hole shadow, but with this method, you're just having a single telescope, and therefore you can go to much larger distances because there's no spatial resolution needed. You just need temporal resolution. Big question is, of course, inclination dependence. The example that I showed was exactly at 90 degrees. That's not only unlikely, there's probably all kind of stuff.
Jordi, you have 2 minutes left.
Yeah, great. There's also probably all kind of stuff in the way that will block the view. So what about like the inclination dependence? So I also varied the inclination for different models. And there I found out it might be hard to see. There's like this yellowish line, which is like 3 degrees higher than 90 degrees. And that's where you start losing the signal. So the window is like a few degrees wide for 100 gravitational radii. But as the binary becomes smaller and smaller, that inclination window actually becomes larger and larger. So the closer you get to merger, the easier it will be to measure it, although you will need higher temporal resolution because the binary will move faster in front of the background. So what are search strategies then? How can we find these things? So the current data seems to favor, because of observational biases, more the higher mass black holes. They're like 10 to the 9 solar mass. The periodicity is typically a year. The dip lasts for like a few days, and the inclination window is a few degrees at most. This is kind of ideal for like observability. Like the dip will take like a few days, so it's not too crazy. So if you then assume that all the black holes are oriented in the sky uniformly, you'll get a probability of like finding it of like 1%. It's like 3 over 90 degrees. So one strategy could be to follow up current candidates. You get like 150 sources, so 1%, maybe there is already one in there. And additionally, find new sources with Vera Rubin's observatory by looking at the LSST, which is like 100 million AGN targets. So who knows how many self-lensing flares we might find in there. And there's, of course, also the pre-merger electromagnetic emission of these sources. And I think I'm running out of time. I have some caveats here. I would be happy to talk about like circle binary disks and how they could alter the signal, but I will leave my summary up and I'm happy to take any questions.
Amazing. Thanks, Jordi. Any questions?
Hey, really nice talk. Just back to spiky again. Like, do we have any handle on what the periodicity of that spike should be? Like, would we expect to see it again in, I don't know, X amount of years?
So the periodicity is actually pretty rapid. It's like a 2-year periodicity. So unfortunately, there were just not a lot of like high cadence data after Kepler. And this is also because Kepler just had exquisite photometry, right? If you look at that, at these like tiny error bars in there. So there is some follow-up work ongoing, like Dan D'Orazio is working on this. There is like quite some like ground telescope data that we've been crunching to try to re-identify where we are in the phase. Also, given it's 2010, right, and the model uncertainty, it starts to shift dramatically the prediction where the spike would happen. So there is ongoing work there, and it should be observable for sure, given that the periodicity is only 2 years. So it should be easy to rule out if this is just a fluke or if it's actually a real gravitational lensing signal.
Okay, cool, thanks.
We have one more quick question, maybe? Or otherwise, let's thank Jordi. Let's try that again. So next we've got Shashank Dattatreya. Take it away, and I'll also give you a 2-minute warning.
Thank you very much. My name is Shashank. I'm a second-year grad student at Yale, and I'm going to be talking about core dynamics and off-center black holes. So Elisa gave an excellent review about what happens during a galaxy merger. Initially, the two black holes are going to inspiral towards the center by dynamical friction. They're going to form a binary, and 3-body interactions with the stars are going to result in the hardening of the binary. Eventually, gravitational wave emission takes over, resulting in coalescence. And then, depending on the mass and spins of the black holes, we can have a recoil kick. And in most cases, we expect that a recoiling black hole is going to be brought back to the center, again, by dynamical friction. Now, since dynamical friction is such an important ingredient in all of this, we should take a closer look. So we have all seen the classic Chandrasekhar prescription of dynamical friction. We have a massive perturber moving through an infinite homogeneous sea of particles, and the motion of the perturber creates a wake behind it, and it's the back reaction of the wake which results in the slowing down. And based on these assumptions, we can derive a simple formula which works remarkably well in most cases. For example, if we have a black hole which is spiraling through a galaxy, we can see that the radius of the black hole very closely follows the Chandrasekhar formula. And of course, most cosmological simulations can't properly resolve the internal processes of dynamical friction. For example, PNG and other simulations instantaneously reposition the black hole at the minimum of the potential well, which can result in all sorts of issues like artificially enhanced accretion and artificially increased black hole merger rates. And other simulations like Romulus and Astrid actually use a subgrid prescription to model dynamical friction. And again, this is based on the Chandrasekhar formula. But it doesn't always work. And as Elisa pointed out, one of the famous cases where it fails is if you have a massive black hole moving through a galaxy with a constant density core. And we can see that after a certain radius, the black hole doesn't want to sink in any further. It stalls at the kiloparsec scale. And this has been reproduced many times, and this is known as core stalling. Now, the next obvious question to ask is what happens if you take the black hole and then put it inside of the core to start with? Then you can see it actually gets pushed out to the core radius and then eventually settles at this core radius where it continues to stall. This is known as dynamical buoyancy. Now, neither buoyancy nor core stalling have been predicted by the classic Chandrasekhar prescription. But then again, galaxies are not infinite homogeneous seas of particles, so that's not really a surprise. Now, of course, we know that several massive ellipticals in the universe today have very flat density cores, and perhaps so do dwarf galaxies. And even if you start out with a cuspy profile, you could transform it into a core through core scouring or recalling black holes. The whole core cusp problem is still an ongoing debate. And so the phenomenon of core stalling and buoyancy could have profound implications for black hole dynamics, for mergers, AGN feedback. And so in this talk, I'm going to be talking about the conditions for core stalling and buoyancy, and a bit about the inner workings of what exactly is going on. And I'm going to be using idealized n-body simulations, which can hopefully give us some insights into the stellar dynamics at play. Okay, so we know that if we have a spherically symmetric density profile rho of R, we can use the Eddington inversion formula to derive the distribution function f of E, which basically tells us about the distribution of particles across different energy levels of the system. However, not every distribution function is the same. If you want a physically realistic solution, we must have f of E greater than 0. And if you want a distribution stable to perturbations, we must have df by dE less than 0. So based on this, if we have a nice cuspy density profile, we can see that the distribution function is always positive and stable at all energies. But then if you start to flatten out the density profile, the resulting distribution function also starts to flatten out, and it eventually develops an inflection point at a certain energy. And then if we make an even sharper core, we can see that the distribution function also develops this kink at a particular energy, resulting in a region of instability. And so core galaxies are more susceptible to inflection points and instabilities in the distribution function than cuspy galaxies. So based on this, we can take a more careful treatment of dynamical friction. Tremaine and Weinberg derived the expression for the torque on a massive perturber due to dynamical friction. This is a complicated looking expression, but the three important terms are there's an integral here over all of action space. And you can think of this as an integral over all orbits in the system. There's a gradient in the distribution function, and there's a Dirac delta function. And this picks out resonance. So according to the Tremaine and Weinberg picture, only resonant orbits contribute to dynamical friction. And then recently, this was revised by Banach and van den Bosch, who included the contribution from non-resonant orbits. So here's the self-consistent torque, which also includes non-resonant orbits. And you can see there's no delta function anymore. Instead, you have this term, which we call the memory effect. I won't talk about it too much. You can ask me later. But if we then use this prescription to take a look at our core stalling simulation again, on the left is the radius versus time of the black hole, and on the right is the distribution function of the medium, and the black line shows the black hole energy. You can see that the black hole very quickly sinks in through the stable part, the df by d less than 0 part of the distribution function. And then when it reaches this inflection point where the distribution function starts to flatten out, that is where it starts stalling. And so we see that different parts of phase space are responding differently to the black hole. Some parts are pushing it in, some parts are pulling out. Now, of course, this is based on the distribution function calculation, but we can go ahead and see what each individual particle is doing and how each particle is contributing to friction or buoyancy. So we know that if the black hole sinks in, then it's going to lose energy, which means that the surrounding particles will gain energy. And vice versa, if the black hole is pushed out, then the black hole will lose energy and the surrounding particles gain energy. So over here, I'm plotting the final energy versus initial energy of all of the particles, color-coded by the instantaneous radius. So let's go ahead and see what happens. We can see that there's a distinct set of particles which all lose energy and therefore contribute to pushing out of the black hole. And then there's another distinct set which all gain energy, therefore contributing to the black hole losing energy and getting pulled in. And it's the net effect of all of this which eventually dictates the motion of the black hole. However, the particles don't just either lose or gain energy. Instead, we can see that each particle is continuously oscillating between losing and gaining energy, and therefore each particle is contributing simultaneously to friction and buoyancy across time. And if we look at, these all are the near resonant orbits with the black hole. They are librating with the black hole, and it's the interaction between the stars and the black hole which eventually leads them to the motion. So here is one such resonant orbit. On the left is the orbit, and the right shows the energy of that particle versus time. So initially, it's on a nice elliptical orbit. The energy is fairly constant. And then eventually, it's going to interact with the black hole and then suddenly get pushed out, gaining energy. And so the black hole loses energy, contributing to friction. But then later on, that same particle is going to get pulled in. Therefore, the black hole gets pushed out because of this particle, and vice versa. It continuously oscillates between pulling in and pushing out of the black hole. And this is one such resonant orbit. Every orbit which is on resonance with the black hole is doing the same thing. And it's the gradient in the distribution function which determines the number of gainers versus losers, which determines friction versus buoyancy. And when we have the number of gainers equal to the number of losers, that is when we get core stalling. And now I will very quickly touch upon recoiling black holes. So here are two galaxies, same mass, same radius, just different density distributions, and same black hole mass as well. So let's see what happens if I give a black hole a kick in a cuspy galaxy. You can see that it very quickly comes back to the center. And this is because dynamical friction is very efficient in cuspy galaxies. But on the other hand, if we give the same black hole the same velocity kick in a chord galaxy, it takes a significantly longer time to even come back close to the center. And even when it is close to the center, it's still oscillating, and it's essentially stalling near the core radius. So this raises an important question. If we have a recoiling black hole which kicks out stars in the center, transforming a cusp to a core, then does this mean that dynamical friction itself is self-limiting? Will we have recoiling black holes come back to the center in chord galaxies? So I'll just leave up my conclusions here. High-resolution simulation N-body simulations can reveal a lot of interesting stellar dynamics at play. In particular, the difference in the dynamics between chord and cuspy galaxies. We think that these phenomena like core stalling and buoyancy, they are real physical effects which are driven by near resonant effects between the stars and the black hole. And it's this gradient in the distribution function, we think, is what determines the number of gainers versus losers and eventually dictates the motion of the black hole. Now, of course, these are N-body simulations, And so it's an open question about whether this, how applicable these are in the real universe in massive ellipticals or dwarf galaxies. But clearly dynamical friction is much more complicated than we thought it was. And so perhaps insights from idealized simulations can help. Thank you.
Okay, we already have the first question. Oh, first two. Well, we'll get to both.
Thank you. This is really, really nice. I love this self-limiting dynamical friction from the black holes after the core. So I have two related questions. So perhaps I missed it, but is the model that you're using spherical or triaxial?
This is spherical.
Okay, so my question is, would triaxiality or having more eccentric orbit matter? I mean, you should, the recording black hole probably had an eccentric orbit at least at the beginning. So I was just wondering about triaxiality, eccentricity, and how they change the picture a little bit.
I am not sure about triaxiality. I'm not sure about how triaxiality changes because it's much more complicated to analyze. Like we can't do a simple Eddington inversion to get the distribution function in a triaxial system. But with respect to eccentricity, like here is like the simulation where the recoiling black hole is given a completely radial kick and it still stalls. There are some very interesting dynamics which result in either the gaining or losing of the eccentricity during core stalling and buoyancy. I would love to chat about this later, but also in the first simulation I showed with buoyancy, the black hole isn't on a perfectly circular orbit, it is on an eccentric orbit and it still stalls near the core radius. So I'm not sure how much eccentricity would help, but that's also an interesting thought. Yeah.
Great. One more quick question.
Yeah, really nice talk. Thanks. So I was wondering, at this stalling radius, if the initial black hole in the galaxy is already located there, when a second black hole comes in, would the binary form at this radius, and would that be a stable configuration?
At the kiloparsec scales, well, if you have a binary forming at this scale, then it's going to kick out stars due to core scouring itself. And so I think that if you have a binary at the kiloparsec scales, you can transform a cusp into a core and therefore severely reduce or increase the dynamical friction time for in-spiral.
Thank you.
All right, let's thank Shashank again. Next up, we've got Erika Ogata. Okay, let's close this. How do you, this one? Yeah, you can use that for clicking if you want. Is that working? There's one clicker and one pointer. So I think maybe this is, let's test it when yours is up. Big presentation. So play. Is that one working? Is it on? No, it's not. Let's see. Or how should I use this one? I mean, you can just use the laptop. Okay. I tried to get Avi to look at it. Sorry.
Okay, thank you for giving me good opportunity and great organizing. So today I would like to talk about the three-dimensional radiation hydrodynamic simulations of wandering seed black holes. I forgot my name. I'm Erika Ogata from University of Tsukuba in Japan. And we are interested in the formation process of supermassive black holes. As you know, there is a strong relation between its mass and the mass of the host galaxies. And also, our latest observation suggests that such supermassive black holes exist at even the hazy universe. So how are these well-known supermassive black holes produced? This is a still open question in modern astronomy. And according to a lot of the theoretical scenario, and first of all, the seed black holes pass around the redshift equal 20 or 30, and then it are expected to float in the dusty remnant galaxy after the galactic merger. So, and in general, we call this accretion mechanism as Broglie-Hoyle accretion. So, here we investigate the mass accretion rate onto the moving seed black holes, and I mean the more accurate Broglie-Hoyle accretion rate. So our students are comparing with the previous studies of Broglie-Hoyle accretion flow as considering the anisotropic radiation field and the sublimation of the dust grains. And in general, the accretion disk formed around the black holes produce the anisotropic radiation field, and such strong radiation is expected to hit and sublimate dust grains. So it's important to consider both of them, but however, there is no previous studies and in which simultaneously take into account the both of them. So here we try to perform the three-dimensional radiation hydrodynamic simulations under the anisotropic radiation field, and we also consider the sublimation of dust grains. And the simulation code used in our works is a SMART M1, which is a radiation hydrodynamic simulation code with adaptive measurement scheme. And the basic equations are shown here, and also the radiation transport is calculated by a momentum-based scheme. So, and actually, we also take into account the chemical network of 11 species shown here. And indeed, we mask the black hole accretion disk by the sink region due to the huge computational cost. So I mean that we just inject ionizing photons in the sink regions with anisotropic radiation, anisotropy distribution, the cosine function. The other settings are shown here. For example, the size of the sink region is said to be sufficiently smaller than the size of the dust sublimation region, and the size of the computational domain is said to be larger than the ionized region. So, and also we assume that the barometric luminosity of the accretion disk is roughly proportional to the mass accretion rate onto the sink region. So to run the simulation, we adapt the rest frame of the sink region. So the gas flows in from the upper boundaries of simulation box, and at the upper boundaries, we set the metallicity to the 0.1 solar metallicity, gas temperature to around 200 Kelvin, and the velocity to the 20 kilo per second. And also, we have already performed the other simulations. These values, we adapt these values as the simulation parameters, but today I only talk about the simulation result with simulation parameter, the gas number density and the black hole mass. So before I talk about our results, I show our schematic view of the simulations. So, first of all, ionized region like two spheres glued together at the equatorial plane formed around the several parsecs, and the dense shock shell formed at the ionization front. The sublimation of the sublimation region extends up to around several AUs. And in that region, the radiation force is ineffective, and so that the dusty gas can accrete easily. And from here, I mentioned about our result. First of all, mass accretion rate. So, and the left figure shows that whether superhélical accretion occur or not. And the vertical axis and the horizontal axis mean that the black hole mass and the number density of the gas. So from this figure, it's clear that the seed black holes can undergo the superhélical accretion state if the product of mass, black hole mass and the number density of the gas is larger than the 10 to the 10th solar mass per cubic centimeters. So this result suggests that we need to change the upper limit of the mass accretion rate in the cosmological simulations, because in general, the Eddington limit are adopted as the upper limit of the mass accretion rate in cosmological simulation. However, our simulation results suggest that if this condition is satisfied, the super-Eddington accretion state can emerge. And we also found that such super-Eddington accretion rate occurs only by gas accretion near the equatorial plane. I show the gas number density distribution and the ionization degree distribution middle side, and we confirmed that the gas inflow gas just passed through the ionization front rose up due to the strong radiation force near the disk rotation axis. On the other hand, near the equatorial plane, the flow structure is similar to the classical bonded Hole-Little accretion rate. And also, I show that the time dependence of the mass accretion rate on the right side. So we found that the mass accretion rate oscillates because the dense shock shell on the equatorial plane is collapsed due to the strong ramp pressure of the H1 gas. And here I would like to mention about the acceleration of pseudo black holes. We calculate the acceleration of pseudo black holes using this formula. And in this equation, the first term means the acceleration due to the gravity of the high density shock shell. And the second term means the acceleration due to the momentum transport to the pseudo black hole via gas accretion. And also I show the right figure shows that whether pseudo black holes speed up or slow down. So from this figure, we found that the pseudo black hole could be accelerated due to the strong gravity of the high density shock shell upstream. So I mean that in this equation, the first term is more effective compared to the second term. And finally, we talk about the evolution of pseudo black holes. So here we convert the accretion rate and acceleration to the time scale of mass growth and the velocity change. From our result, in any situation, the time scale of velocity change is sufficiently smaller than the age of the universe at height universe and the time scale of mass growth. So these results suggest that any pseudo black hole change the velocity first and grow in mass later. And also we found that only if the product of black hole mass and the gas number density is larger than the 10 to the 9th solar mass per cubic centimeter, the time scale of mass growth is sufficiently smaller than the age of the universe at the height of the universe. So, and what I would like to say that here is that pseudo black holes could grow into supermassive black hole until redshift near or equal 6. And there is 2 pathways on the black hole mass and the velocity plane. So one is no mass growth path, and another one is if this condition is satisfied, the seed black hole can grow rapidly. So maybe there is no time. So at the end of this talk, my talk, I would like to mention about the future work. And because, okay, thank you. And because of the huge simulation cost, and this study aims to understand the gas accretion mechanism at the only sub-parsec scale. So, and as a result, we suggest that if the product of black hole mass and the gas number density is larger than the 10 to the 10 solar mass per cubic centimeter, the mass accretion rate is sufficiently larger than the Eddington limit. And on the other hand, I didn't talk about today, but we have already performed the simulations in other situations. And as a result, we found that if the product of black hole mass and the gas number density is sufficiently smaller than the 10 to the 10 solar mass per cubic centimeter, the mass accretion rate is smaller than the classical Bondi-Hoyle-Toot accretion rate. So maybe I remember 0.1% of the classical Bondi-Hoyle-Toot accretion rate. So what I would like to say here that is boost factor and the condition of the upper limit in cosmological simulation should be modified to be more realistic. So, and we recognize that we need to consider the event horizon scale phenomena. So, so this is my future work. So we will simulate iteratively between the parsec scale and event horizon scales to make a new Bondi-Hoyle-Toot formula. I mean that if someone gives a gas velocity and the gas number density or something, we can get the accretion rate from our formula. So, and then we hope that if I can, we adapt our result to the cosmological simulations. So yeah, that's all. Thank you.
Any questions?
Hi, very nice talk. I was wondering about the density you assume for this study, because I was thinking that if the black hole is wandering out of the galactic center, the typical density should be much lower than 10 to the 3, so, which means that very likely you are not a super Eddington. So, especially if the black hole is low mass, because your criterion is 10 to the 9 for the product between mass and density, which means 10 to the 6 for a 10 to the 3 mass solar mass black hole.
Yeah, I agree with you. But and in this simulation, just assume that this gas number density. But I think there is a how can I say? So. Okay, sorry. I think it's enough. Sorry, I can't explain. And so yeah, I have I can explain in Japanese. No, but so I will later to tell you about my idea. So yeah, but I agree with you. So, but I have good results to you. So I'm
no, because I was simply wondering whether you were thinking maybe, I don't know, the black hole wandering inside a very dense gaseous disk or a molecular cloud where you can reach those densities. Because in typical ISM condition, probably it's very unlikely to reach this regime.
Yeah, I think so. But how can I say? The supermassive black hole at the height of the universe is very rare compared to the total amount of the black holes. So I think we, how can I say? Yes, so sorry, I will tell you later.
All right, maybe something for the coffee break, because more detailed discussion. Okay, one more quick question whilst the next speaker sets up.
Thank you. This is super interesting work.
Thank you.
So yeah, it's really interesting to see that black holes can actually accelerate rather than decelerate for many of the parameters, many of the simulations. So I was wondering, when the black hole is accelerating, then I guess higher velocity, does that mean also lower accretion rate?
If the high velocity, in the high velocity case, the flow structure is similar to the classical Von accretion. So the black hole could be not accelerated. So yeah, that's my result.
Okay. Thank you.
Sorry. Yeah.
Okay, let's thank Erica again. See, it's working now. Okay. Let me not share your whole presentation, but the clicker should be working now in theory if you want to use it. Thank you. All right, next one, Yan Chen.
Yeah. Hello, everyone. Okay, thanks. Hi, everyone. I'm Nian Yi. I'm a final year grad student from Carnegie Mellon University. And I want to thank the organizers for organizing this amazing conference. I've learned so much in the past few days. And so during our discussions in the past few days, one theme that keeps coming back is the idea of bridging the gaps in the simulations and to be able to really fully model the physical process that drives the black holes at all scales. So today I want to continue along this theme and tell you about how we can bridge the gap between the large scale dynamics with the small scale dynamics of massive black hole mergers. So this work is done with these wonderful collaborators, and I want to let you know that we'll post this work is finished, and we will post the paper on arXiv next week. So stay tuned. The middle one. Oh, okay. And this morning, Elisa has already given us a very thorough overview of this full dynamical range that the black hole go through, from large scale structures, galaxy mergers, all the way to binary formation and the coalescence. So I'll not repeat this whole process, but here just to give you an idea of what physical process drives the orbital decay in what scales. And previously, what has been better understood is probably the process of the stellar scattering regime and the gravitational wave regime, because these processes can be simulated with idealized n-body simulations and theoretically modeled. And for the large scale dynamics, for decades, it has not been treated very carefully. And I will show you an example here. That, for example, this is what a lot of cosmological simulations will do to the black holes. So the way they're treated is that they're always repositioned at the galaxy centers. And so when two galaxies merge, the two black holes will just be immediately stitched together in this case. And so this is not a very faithful modeling of what will actually happen when galaxies merge, because the black holes will in-spiral instead of merge immediately. So with this in mind, we developed this subgrid modeling to incorporate the dynamical friction from both gas and stars in the asteroid simulation. So this leads to this more realistic modeling of the orbit. So you can see the black holes are actually going through the orbital decay driven by dynamical friction after the galaxy merger. So with this, we have a more realistic prediction of how the seed black holes will actually behave, because as we've discussed yesterday, the seed will not always sink to the center and merge efficiently. So this leads to a lot of wandering black holes in our simulation that Yueying will probably tell you more about later. So if the seeds don't merge efficiently, will they still merge at all? And the answer, at least from Astrid, is yes. So in Astrid would predict that the massive black hole mergers are still dominated by these seed assembly events. So this gives us hope to actually find this seed at high redshift. However, we all need to acknowledge our weaknesses. So one thing that I want to review to you is that in cosmological simulations, actually, we do not have a very good prediction power to the seed merger regime just because of the numerical limits in these simulations. So as an example, this is one of the seed merger events in Astrid. So this is a high redshift dwarf galaxy merger. And you can still see the orbit of the black holes, but at the same time you can see the discreteness of this potential, and the host galaxy is actually not modeled by a lot of star particles just because they're so small. So in this case, it's still like a question of, if we merge the seed black holes in Astrid, are they real mergers, and what happens to the later orbital decay? So going back to this original picture, we resolved this large-scale orbital decay by the dynamical friction subgrid model. But the question is our coarse resolution dynamics robust for the seeds? And a following up question is, the dynamical friction actually drives the binary hardening, drives the binary formation to further, and these are the scales that we cannot model in cosmological simulations. So what will happen next? So with this in mind, I developed this resimulation technique, which is able to simulate the black hole merger directly drawn from the Astrid simulation, but at much larger scales. So this is how this is done. So we take a merger system from Astrid, and then we trace it back to before the galaxies merge. So you can see in the first frame, the black holes are separated with a lot of galaxies, with some galaxy stars and gas around it. And what we do is we mimic this system, the exact configuration of the merging galaxies and the profiles, the mass of the gas, the dark matter and stars, but at much higher resolution. So we increase the resolution here by more than 1,000 times. And then we evolve this system so that we can trace the dynamics of the black hole to at much better resolution. And we even account for like the new infrastructure that surrounds this merger system. And this shows that we're able to exactly capture the galaxy properties of this merging system. And then we also increase the resolution by 1,000 times. So we not only do one system with this technique, we actually sample, do a statistical sample of 15 systems across this parameter space of host galaxies and black hole mass. And here I just show you in one of the resimulated system. So here is a galaxy merger, and now we're able to really trace the black hole down to the binary hardening regime. And also the resimulation system actually reproduced the large scale orbitals decay of the Astrid system very well. So what can we learn from all these gain resolution? So the first question we can ask is, what happens in this breach scales, in the scales that in the scales of the orbital decay that Astrid cannot resolve? So one thing that we found is that during the course of this orbital decay, the galaxy actually grows by quite a lot before the black holes enter into the hardening regime. So in general, you can see the central stellar density grows by a factor of 2 to 3 during this full dynamical range. And this is important if we want to consider the subsequent hardening mechanism. And also, we found that high central stellar density and star formation is key to driving the black hole towards coalescence very rapidly. And another conclusion we have is that we find that in general, the orbit of the black holes were circularized during the dynamical friction regime. And we see a clustering of eccentricity around 0.8 when the black holes begin to bound. And finally, if we have, so these are the in the cases in which the binary completely, the black holes completely stalls in the resimulation, and these are all dominated by the by the moderate to low eccentricity systems. And finally, one result that I'm very excited about is the sinking efficiency. We found that the sinking efficiency of the binary is actually driven quite a lot by the initial phase of the orbital decay. And this is good news because then we have some hope of actually modeling this subsequent dynamical friction time, even with the limited resolution in cosmological simulations. So here we see that in the top, we show the orbital size evolution of the merged systems. And we see that even within the first 200 mega years, which is almost completely resolved in asteroid, you can tell the fate of this binary to a pretty good extent. So here we see that for the systems that merge or begin to bound in the resimulation, we see this large-scale torque-driven orbital decay that efficiently brings the black hole down to below KPC scales, after which the dynamical friction becomes efficient due to the high central stellar density and star formation rate. So these are the systems that can merge efficiently. Whereas for the stalled system, even at large scales, you see that the black holes never enter into the final KPC scale. And so the dynamical friction actually never becomes efficient enough to ever bound the black holes. And so it's very exciting to see that there's truth even in the coarse grain dynamics modeling of asteroid. And so we can actually use that to make more robust predictions for the subsequent merging timescales. And a final result that I want to share with you is we not only model the two galaxy mergers, but we also model these more complex systems in denser environment and more gaseous environment where multiple black holes will encounter each other in these mergers. And we found that in all these very complex mergers that has a lot of infalling gas, the black holes will almost always stall on KPC scales. So the wandering black holes that we found are mostly coming from these systems. So you see these, like all of the, so here we have 4 black holes in the system in the subsequent mergers, and all of them stall in KPC scales. So that poses a problem for the seed growth in this regime. And finally, I want to mention our future ongoing work, which is to actually go even further. So now we kind of bridge the gap between the cosmological simulation and the binary hardening phase. So our next step is to actually feed the end state of our resimulation as the initial condition for small scale binary hardening simulations. And so we're already starting to do some of these. So for example, here we take one of my resimulation end state in which the black holes kind of stalls on KPC scales, and we explore whether by embedding them in dense stellar clusters, the black holes can sink to the center more efficiently. So here our preliminary results shows that if we embed these in stellar clusters of mass roughly 5 million in solar masses, then the black holes will merge efficiently, will harden efficiently. So thank you. I will leave our conclusions here, and I'll be happy to take any questions.
Great. Any questions? Okay.
really awesome talk. I was thinking about Shashank's talk and basically thinking about whether you have seen the halo profiles of some of these black holes and if that contributes to the stalling of the merging.
Yeah, so we have looked at the profiles, and in our case, I think the profiles are more, yeah, they are actually more core-like. So we haven't, I think at our current resolution, it's still kind of hard to exactly resolve what happens in the middle region, but it would be interesting to explore by, like, for example, we can push this to actually higher resolution because these simulations are not so expensive. So if we do that, we can study that in more detail.
Thanks, Diani. Really interesting. So I was wondering, when you do these high resolution runs, do you use the same ISM physics as the original asteroid simulation? And if you were to, say, use a different, more multi-phase explicit ISM simulations, how would that impact your results?
Yeah, so I think that's a very key point, and that's a very interesting question in the direction that we want to take in the future. So currently, yeah, we're still using this more like smooth version of the ISM treatment, and I think it will definitely have impact on the dynamics of the black holes, because if you have multi-phase ISM, then you'll probably see more of those like clumps, cold clumps that will maybe scatter the black hole more, so it will pose more problem to the sinking. That's my expectation.
Thank you.
All right. Okay, one quick question.
Thanks. So I saw in your plot that any black holes that circularize too much stall. Is it obvious why this is?
Yeah, so in general, the dynamical friction driven energy loss is sensitive to the orbital eccentricity, and so it is predicted that even in like analytical forms that like low low eccentricity orbit will go through less efficient orbital decay in dynamical friction. And also for the circular systems, actually, because because they're circular, they tend to have wider min, so they have like wider paracentric passages, so they actually never go into this dense stellar density in the center. Yeah.
Thank you.
All right, let's thank all of the speakers from this session again.